So I'm the kind of geek that does diagrams of his home network. And actually, the reason this diagram exists is because my wife said, well, if we get a divorce, I won't know what the hell you were doing at home. And then I said, challenge accepted, not to the divorce. Uh, and then I just made a diagram because, well, why not? So let's start. So, well, even though it's about tinkering with my home internet connection, that doesn't mean that it started out as being bad. So this is a screenshot from speed.cloudflare.com, and you can see that the results at the bottom are not actually bad. It says great, so I expect it to be great. But the goal of our speed test, of Cloudflare speed test, is to report on the behavior you should expect to have, like in your realistic use. So it's not actually a tool for measuring the network like a network engineer would measure. It's what you as a user should expect. So these numbers look good, but if I scroll down the page to the details of each one of the tests, you can see there are a few outliers there. So even though the unloaded latency is under 5, it sometimes goes up to 30. There's at least 1 or 2 outliers there. I think it's 2 points, 2 dots. The same with the latency during download, but the latency during upload is much worse. So it kind of stretches out into the 60 milliseconds range and then has an outlier out there in the maybe 150, which is not very good. So the issue with latency is twofold. One is, well, it may impact stuff that's more real time, like gaming. It's the most obvious example always. Like if you have lower latency and more stable latency, you may get shut down less often. But also the latency also limits your bandwidth. So usually when you are browsing the web, your browser is doing many small requests. And when doing those small requests, so if you think about TCP, how TCP works, when a connection starts out, it sends a packet, and then it gets an acknowledgement for that packet, and then it sends the next packet. And then it sends 2 packets and waits for 1 acknowledgement, and then it sends 4 packets and waits for an acknowledgement until it reaches a point where it loses a packet, and then it says, what, I went too far, and it goes a bit back, and then it starts doing the same thing over and over, but linearly. So that beginning part, that exponential part, is called the TCP slow start. So during that TCP slow start, you cannot get more bandwidth than what your latency of the packet going there and getting an acknowledgement back allows you. So it's possible that you have, like I have a 500 the megabit connection from my ISP. I may have a friend with 100 megabits, and if his latency is better than mine, he may get a faster browsing experience than I do, even though I theoretically have a better service. So that's why that's one of the reasons why latency is important. And the other one is, well, you don't want to get shot in the head in games because your latency spiked. But so if you want to stress out your network, so if you want to really see what your connection can do, there are other tools. So if you are on Mac OS, if you are using Mac OS, there's a tool that comes bundled in, which is called Network Quality. I don't recommend running this tool while you're in a call, because it will bring your call down. It will really stress your connection. But if you are not on Mac OS, there are a few alternatives that use the same measurement algorithm. One of those is Go Responsiveness. The other one is a tool made by Cloudflare called Network Quality RS from Rust. And if you want to see the details of how the algorithm works, which is designed by a few folks mostly at Apple, but not just at Apple. You can see that draft from IETF. So looking at these numbers, the most important thing are the RPM numbers. So RPM doesn't mean anything. It's a kind of a unitless thing. It's bigger is better. But out of these numbers, one stands out for being much lower than the others. So that's the one we want to bring up. We want all those numbers to be close together. That's our goal. And the secondary goal is I want to be in a video call, run one of these tests at the same time without a glitch. That's the goal. So if you want to optimize something, you need to have some way of knowing if you got there or not, or how far away you are from that goal. So what about Wi-Fi? Well, Wi-Fi is kind of a different problem because in reality, you cannot fix Wi-Fi because Wi-Fi is kind of lives in a sea of dragons. Your neighbors, interference, all kinds of stuff. The things that I'm going to talk about help the quality of your Wi-Fi as long as you are close to your access point and stuff like that, but it doesn't fix it. This would be a topic for another day and probably a much longer presentation with all sorts of caveats and stuff. So back to our goal, we want to bring that 341 number up and bring those 175 milliseconds down. Also, I should note there's another tool to test for this stuff. It's quite recent. By Cloudflare, it's called BBPerf. It's very, very new. So this is kind of what your connection may look like. So on this end, it's your home. You may have your devices. If we are kind of assuming you have devices connected through cable. That's the assumption for this presentation. So you may have a bunch of devices connected, most likely via gigabit connection to your router. But then, and your ISP has a pipe on their end, which is more than a gigabit, that is supposed to serve you and your neighbors. But the link between you and your ISP is probably under that value, or at least at that value. And it's probably, it's being limited by your ISP. On my case, since I'm on a 500 megabit plan, so it's half the actual link, which is a gigabit. Your ISP is either limiting you on a device that they have on their end that shows your traffic. If you go above, it starts dropping stuff. Or in other cases, it may be happening on the CPE. And the CPE is the customer premises equipment. It's what they call to the router that they place in your house. But in either case, you don't have any control over their device or the device they put in your home, at least not this level of control. So this is the problem. The problem is the bottlenecks. This is where traffic, like if you imagine a highway, cars going through to an exit, if there are too many cars, they will back up. And unlike packets, you cannot just pulverize cars and make them disappear. So at those choke points, at those bottlenecks, the queues will exist, queues or buffers. So buffers are a good thing. You need some buffering to smooth out spikes. So you don't want to just be, if a packet cannot leave immediately to that narrower link, you don't want to drop the packet immediately. You want to buffer it for a while. So queues are a good thing, but as long as they are not too long. If they are too long, something called Bufferbloat happens. And you can read that introduction, although I'm going to talk a bit about what Bufferbloat is. So if the queues get filled up, so you have a lot of traffic trying to go out through a narrower link, packets will start queuing up until they kind of reach the maximum size of the queue. And at that point, you have congestion. You cannot accept any more packets. So you start dropping those packets. And if those queues stay at their maximum size for a while, it's called a standing queue. And standing queues are bad. Standing queues are bad because, well, packets start to get dropped. So TCP connections start reducing their output. but there are other consequences. If there are multiple flows, they may synchronize and they may not be able to, when they are trying to reach the maximum of capacity of the link again, they may not reach it, and then you underutilize your link, which if you're paying for it, you want to be able to use it. So to solve this, we need to control what happens inside the queue. We want to have shorter queues because a long queue adds latency. When a packet is in a queue, it will, well, add time until it reaches its destination. So we want to have a relatively short queues. And we also want to have a smart way of deciding when to drop a packet or not. So because dropping a packet is a signal to don't push too many packets. So that's a good thing, but you need to be able to control that and use that signal wisely. The latest, there are a bunch of algorithms to manage queues, some simpler than others. The latest ones or the smarter ones are what's called CoDel and CAKE. So CAKE is kind of an improvement over CoDel. And what they try to do is roughly ensure that a packet doesn't sit in a queue for more than a certain amount of time. So you accept adding like a few milliseconds of latency, but if a packet has been sitting in a queue for much longer than that, you drop it. And the hope is that, well, like it shows in this diagram, if you have a flow that's sending many packets and another one which is sending just a few packets, that things are fair. And well, this also includes having more than one queue, like splitting the queues, but I don't want to go into that complexity because that's a, well, very deep rabbit hole. And I don't have hours to spend on talking about it. So CoDel or CAKE. Another complication. Well, inside on your network interface, there are actually more than one queue. There's the queue that you can control, which is the kernel queue, where you can apply CoDel or CAKE. But there are also queues inside the device driver and inside the network card. And the reason why these queues exist is because you want to move packets from one layer to another, like in bigger chunks. If you do that, you reduce CPU load on your machine. But as you do that, the packets going to the other queue, and then you don't have control. And these queues tend to be first in, first out queues, and with at most you can control their size. And in like consumer equipment, maybe not even that. So you want to be able to indirectly control this as well, using CoDel or CAKE. So first thing you need to do, you need to have something you can control. So you need to have your own router. I'm not going to recommend you any specific equipment, even though this is mine, but this is maybe around 9 years old now, and it still works just fine for what I needed to do. You can go to OpenWRT. So another thing is you don't want to use the firmware that comes with the router because they tend to not be, I'm going to say you tend to not be able to control a lot in there, and I just leave it at that reason. So if you're going to install a different firmware on it, the one I use is OpenWRT, which is fairly mature and supports a very large list of equipment. If you go to that table of hardware, which is the first link in there, you can look at those there and see their characteristics, and then you go to wherever you want to buy a router and choose based on that. Another thing I recommend is not building your own firmware, but building your own firmware bundle. Because if you want to install extra packages, and we will need to install extra packages to do to manage those queues in a smarter way, you don't want to install packages on top of an OpenWRT installation, even though many people do this, but it will eventually come back to bite you. And ask me how I know later. So I made a script that automates building a firmware bundle. You just give it what's your router model or type, and which packages you want to add to the base firmware. Then you run make, and it does its thing inside a Docker container. You can find it in that OpenWRT build repo there. So this ends up being my setup. So I have my own router connected to the ISP router, which in turn is connected to a device called an ONT that converts from Ethernet to fiber. I still have one of those installed. I don't have an all-in-one router from my ISP, even though my ISP regularly asks me if I want one, to which I say no. And my router has its own public IP address because they allow doing that. They're bridging one of their ports so that my router is, for all effects and purposes, connected to the internet. One important detail is, like I said, if you are not moving packets in chunks between the kernel queue to the device driver queue to the hardware queue, you will spend more CPU cycles. So that means more interrupts, and you need to be able to serve those interrupts faster, which means that your device's CPU will cap your throughput. And the router that I have, this one, has two ARM cores at 1.6 gigahertz, and it's able to go up to around 750 megabits per second. Above that, and the CPUs are at 100% serving interrupts and cannot deliver more. So that's a big caveat. You need a device with enough CPU horsepower to handle your connection. If it's, in my case, if it were gigabit or above, I would need to buy one newer router. But buying a newer router every 10 years, it's not, I guess, not too bad. So once you have OpenWRT installed, and with that package called LuciApp SQM from Smart Queue Management, the first thing you will need to do and come to terms with is that you will have to sacrifice some bandwidth. Because for you to be able to control the queues need to happen on your device. So the bottleneck needs to be on your device. So you need to cap yourself to a speed under what your ISP gives you. And what that sacrifice is not an exact science. You need to try some numbers and see how far can you go without sacrificing too much. So if you look at this, I'm limiting my ingress, so the download speed to around 538 megabits and the upload to 128. And what I actually get after configuring this is up to 500, and on the upload direction up to 120. So it's not even exact depending on the direction. And maybe the reason is that when you are sending packets out, you have queues on your device. But when the packets are arriving, well, they are arriving. If they arrive and you don't have a place to store them, you have to drop them. And you don't have a queue that can be managed. And what this package, this LuciApp SQM package also does, or one of the scripts that comes with it does, is create a virtual device driver that creates an inbound queue that it can manage. So this is to say that there's a bunch of complexity under this, bunch of knobs that need to be picked, but you don't have to think about it, because after you select your sacrifice, your sacrifice in bandwidth, then you need just to select which algorithm you want, if it's CoDel or CAKE. Usually by default, we'll choose CAKE, which is the most recent one, except if for some reason or another it doesn't work well on your device. And the other thing you need to choose is the script that does the setup of all the traffic shaping and stuff underneath. And you have a few choices, one more complex than others, one that do prioritization, others that don't do prioritization. Well, in my case, I went with the simplest of the simplest, and it works just fine. And you can see what the scripts do if you go to that GitHub repo, and you can see, well, a lot of details about smart queuing in that wiki page from the OpenWRT project. So what are the results? Well, in terms of the big numbers, we see that I lost in bandwidth. actually the latency in idles went up a bit, but I think it's within the error margin. The numbers kind of oscillate between 4 and 6. But the loaded numbers, the smaller numbers under those, like latency jitter, the loaded numbers, they went down, and the jitter ones went real down, like under a millisecond. And jitter is the variation in latency. So it's the difference between the latency of this packet and the latency of the next packet and the latency of the next packet, like the average difference. And you not only want lower latencies, but you also don't want your latencies to go all over the place. So jitter is a very important measure, but anything under like 15 milliseconds is passable. I'm not saying good, but it's usable. If it's too high, it may, like your video calls may become really unusable. But the big numbers also, and the drops in bandwidth are not actually real, because what ISPs also do very often is they allow you to go above your limits for a while. And if you keep pumping data or pulling data, they will push you down into your limit or a bit under that limit. So that 533 number is not that stable if I keep doing tests or I keep doing pushing traffic over the network. But that 475 is much more stable. So sometimes it goes up almost to 500, but it doesn't go down as I do more tests. And also, this is the results from before with those outliers. And if you look at the scale there, they are all matched up, so they have the same scale. They have 120, but they are now in a max 12 scale. So I didn't see any latencies up above 12, and they are much more concentrated. So the quality is better. And the results of network quality have improved a lot. So the numbers are now all matched up, and the drop in capacity wasn't that much. And also, the goal of being able to be in a video call and run a network quality test at the same time and not have any drops, well, that works now. I've done that when I was testing this plenty of times during our daily meetup, daily syncs in the morning. So nobody complained. And I also can run the same test at the same time in another machine with just like sometimes it glitches slightly. But more importantly, if I'm doing something to stress out the network, my wife, which also works from home, won't yell from the other room saying that I'm breaking her calls. Now, having said this, whenever you do a speed test, your results go into a pot. And if you go to Cloudflare Radar, there's a section called quality, where those results, aggregated and anonymized, of course, you can compare your results with the results from your country or from your ISP. So what are other people that are doing speed tests in your ISP? What numbers are they seeing and compare to yours? And also see what's the average quality right now. Well, there's a bunch of stuff there. And also one thing that is interesting in one of these graphs is you can see that, well, most people in Portugal have probably 100 megabits of uplink, either very low, which is probably mobile, or 100 megabits of uplink. And there's a bump there in 200 megabits of download. So that's probably the most popular plan from ISPs in this country also. So there's a bunch of stuff you can see there.